Hi, it's me again. So before the class, I have a couple of announcements. And now I only find about 20 people registered on the Piazza. This is a really good place for you to post your questions, and all the TAs, and including me and a lot of staff, will go there and answer your questions regularly. And also we have our office hour set. It's also posted on Piazza. I think the office hour today is 4 to 5 p.m. in Siglab. Tonight, another announcement is tonight we're gonna hold a Pan-SIGGRAPH movie night. The movie tonight is WALL-E, and everybody is welcome. There will be pizza and drinks over there. And we also have a Pan-SIGGRAPH board application. It's a special interested group in graphics. So if you're really interested in graphics, please go and register there. I think it will be a really nice club for you. And also, they will hold also lots of demo sessions. If you have any of your demo reels, it will edit it for you and make some opinions of that. About a correction of my notation, last class, the notation of positive definite and negative definite is a little bit wrong, so I've just corrected here. It's not a big deal, but it's better to correct it. Okay, so before today's class, I will do a little bit recap of the last class, because I heard lots of students worried about how to apply chain rule to a really complicated function. So here I have a sort of complicated function. It's a square root of a log of cosine x squared. And I want to get the first order derivative of x. And how do we do that? At first, I would say, okay, what a mess it is. I really don't know what the first order derivative of fx, but it's okay. I can write fx as square root of f1x, where f1x is the bunch of the stuff hit there. So I don't care what is really inside it. So it becomes square root of it. Okay, interesting. It's 1/2 of square root f1x to the third. So basically, this is the first order derivative of f1x. And sorry, it's treating f1x as just a one parameter, and then we just have this thing. All right. So this is the chain rule. And also, we don't know what's the first order derivative of f1x is. This one is the log of something that I don't care. It's the f2x. So and then that one becomes the first order derivative of this one becomes f2x 1 over f2x, and also multiply by f2x prime. Yep.
Where does the 3 come from?
Here?
Yeah.
Oh, sorry. Maybe I did it too fast. So this is f1x, the square root of it, or I can write it as an exponential thing. All right? Sorry, there's no 3. Yep. And here we apply chain rule again, and so now f2x is the cosine x squared. So I can do another chain rule. So it's something square. So it's a 2 multiplied by f2x and f3x, where f3x is cosine x, and multiplied by the prime of f3x. All right. So this one is easy, because this is a first order derivative of cosine x. This is a negative sine x. And then I'm just going to copy back the value of f3x, f2x, f1x into the equation. And this is the chain rule. And I believe you will use it in your homework assignment, all right? So, and also I'll talk something about block gradient. So if there is a vector x equals to x1, x2, both x1 and x2 are scalars. And I have a function of x, like a function of x, f, and this is a scalar function. So f is an R2 to R map. And what's the gradient of fx? It's going to be easy. It's the partial f, partial x1, partial f, partial x2. All right, everybody knows that this is the way that we get a gradient. However, now, if I have another vector x, which you can still see that, good. Another vector x, which is a function of x1 and x2. And both x1 and x2 are now vectors. x1, x2 are 3×1 vectors. So this is more like your spring case. If you have two endpoints of the spring, then the system has 6 degrees of freedom because it has two endpoints, and each endpoint has 3 degrees of freedom. And now I still have a function fx which maps from R6 to R. Then what's the gradient of it? I can also write it as partial f, partial x1, partial f, partial x2. And now the only difference is this one is not a scalar anymore. It will be a 3×1 matrix. Something, something, something. And then something, something, something. So because gradient is just a linear operation, so you can take the block gradient as just one term and apply that to your homework assignments. I believe that will make your life much easier. Right? Any questions about it? Nope? Good, good. So after some recap, let's start today's class. Today I will go over two parts. The first one is mainly about linear algebra. I will talk about orthogonal matrix and eigenvalue decomposition and the singular value decomposition. And if I still have time, I will blow your mind to talk about some SVD derivatives. It's how you get the derivative of a singular value decomposition, and that's part of the calculus class. So it's a mixture of calculus and linear algebra class. So first, what is the orthogonal matrix? If I have a square matrix, it's going to be square, and with real values, and I can define the matrix as big U equals to U1. U1 is a vector. U2 is also a column vector, blah, 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 to UN. And each UI is an n×n vector. So U is each UI is an n×1 vector. So U gonna be an n×n matrix. All right. So this is nothing special. We're just to represent a matrix with a bunch of column vectors. But what if those column vectors have some special properties? If UI transpose Uj equals to 0 for any I and different I and j's, and also UI transpose UI itself equals to 1 if it's the inner product of itself. And then we can call the matrix orthogonal matrix. What does this mean? It means for any two different column vectors, if I get the dot product between it, or I get a UI transpose Uj between it, they are 0. It means those two vectors are perpendicular to each other. They're orthogonal to each other. All right. Do you still remember the definition of the orthogonal? If I have two vectors and I have a dot product between them and it gets to 0, then the two vectors are orthogonal. Take an example, the x-axis is 1, 0, 0 in 3D, and y-axis is 1, 0, 1, 0. If you take the dot product between it, it will be 0. So that means the x-axis is perpendicular to y-axis. Right? Yep. And this one is a normalization term. It means I want the norm of all the vectors to be 1. So after those two conditions, I can see any two different vectors will be perpendicular to each other, and also all the lengths of the vectors will be 1. And then, what's the good property of this matrix? Let's see. What is the value of U transpose times U? So the first element, the first row, first column of the matrix will be U1 transpose times U1. All right, because you're transpose the U matrix, so the first row, the first column becomes the first row, and the first row times the first column is the same. All right. And the second element of this matrix is, let me see, it's U1 times U2. All right, transpose. And I can go further. The last one is U1 transpose times UN. And I can also apply it to all the columns of that. So this one will be UN transpose U1. This is a UN transpose U2, blah, 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 to UN transpose UN. All right, it's still an n by n matrix, but this is going to be special. Why? If you see the diagonal terms of this matrix, because all the lengths of the vectors are unit vector, all the vectors are unit vectors. So all the diagonal terms will be 1. And then let's see all the off-diagonal terms. Those are basically the dot product between two different vectors in the orthogonal matrix. So they will be 0. And this part will be 0 too. So it becomes identity matrix. Right? Okay. I want to make sure everybody is still following me. So that U transpose U is identity, which means that U transpose is U inverse. That's the definition of an inverse matrix if the inverse matrix times itself equals to identity, right? So you might have seen this before if you were taking any other classes like computer graphics and computer animation. Do you remember if there's some matrix belongs to this group? Yep, rotation matrix. So why? If I have an arbitrary I have an arbitrary vector x, and I have another vector x tilde equals to U times x. So now I want to see what's the length of x tilde. The length of the x tilde is the square root of x tilde transpose x tilde. All right, so it becomes the square root of x transpose U x. And because we know U transpose U is identity, so it becomes the length of x itself. So that one is to say, after multiplying by the orthogonal matrix, the length of an arbitrary vector is remained. So I won't change any vector in the original space anymore. This is the first thing to go. And second thing, if I have arbitrary two vectors x and y in a space, they can be arbitrary vectors. And I have new vectors x tilde equals to u x and y tilde equals to u y. And I want to see what's the angle between x tilde and y tilde. So the angle between x tilde, y tilde can be seen as a dot product between them, an arc cosine, right? And the dot product between them is x tilde transpose y tilde, which can be written as x transpose u y. And again, U transpose U disappears. It becomes identity. So X, oh sorry, there's an X. So it becomes X transpose Y. There's no transpose. So that one means that if I have arbitrary two arbitrary vectors in the orthogonal space, after times with this U matrix, the angle between them won't be changed. So the angle of arbitrary two vectors are maintained. So that is to say, the matrix can only possible to rotate my space or reflect my space. All right. So if I have any two vectors, and after times the U matrix, this is a linear transformation, and those two vectors become like to this two. So the lengths of the two vectors are remained, and the angle between them are remained too. So you can see any rotation and reflection matrix. Only rotation and reflection matrix can do this. All right. I saw some confusing faces. Is there any questions about it? Oh, so what is the angle between two vectors? If it's in 2D, if this is x, this is y, because I can only draw vectors on 2D, the angle between it, theta, is arc cosine x transpose y. This is because x dot y equals to cosine theta. Right, oh, sorry. There is a normalization term. So x dot y divided by the norm of x and the norm of y equals to cosine theta. And because of the first rule, the norm of x and norm of y will be maintained. So this thing will still equals to this thing. All right. So I made it too fast. Sorry. So that's why the angle between any two vectors are unchanged after this linear transformation. So this is basically an orthogonal matrix. You can geometrically the geometrical interpretation of that is that you have a coordinate system. Then you can rotate and reflect in any kind of transformation that you want, as long as it's purely rotation and reflection. And then the result will be the new vectors, x tilde and y tilde. It's basically just a change base operation. You're changing the base of the linear system, right? Okay. So once we know the concepts of orthogonal system or orthogonal matrices, we can start to our eigenvalue decomposition. This eigenvalue decomposition. Right. So the definition of eigenvalue decomposition is here. If I have an arbitrary square matrix A must be square, and if there exists a vector x, so A times x equals to lambda. Lambda is a scalar, 1 by 1, times x, for a non-zero x vector. Then we call x vector is an eigenvector of the matrix A. I will write it down. So x is an eigenvector of A. All right. So so it's like the multiplication of matrix A yields a constant scaling of the vector x. If I'm going to draw it in 2D, if there is a vector x, after the multiplication of A, it becomes like this. So the direction of x then changed. Well, change is the opposite. So it's still a constant scaling factor of x. Maybe it's a negative 3x or something like this, and the lambda is an eigenvalue of a corresponding to x. All right. So what does this eigenvector and eigenvalue mean? It shows a property of the matrix A, because A times a vector x will be a linear transformation, and we really want to know what the property of those kind of linear transformation will be. So for example, if there is a sharing linear transformation, so it changes a square multiplied by 1, 1, 0, 1 by this matrix. This is my A matrix. So what it will be, the x of all the things will be like x will be x plus y. So it becomes this. So it's basically sharing the original rectangular into a new shape. All right. So then I want to find one eigenvector of it. So I would say the x-axis 1, 0 will be an eigenvector of it, because the matrix 1, 1, 0, 1 times 1, 0 is still 1, 0. Or you can say it's the 1 times 1, 0. So that is to say 1, 0 is one of my eigenvector, and the corresponding eigenvalue of A is 1. It means that under this linear transformation, all vectors that is parallel to x-axis, they won't be changed. All right. So you can see that the eigenvectors are not unique. If you times to 2, it's still a valid eigenvector. But the eigenvalue is constant. It's always 1. All right. So then we know that the eigenvectors and eigenvalues of a matrix has their own meaning. The eigenvector means there is some unchanged part under the linear transformation, and the eigenvalue calls you that not unchanged part, it's a scaling changing part to a linear transformation, and the lambda tells you what the scalar it is. And we want to know how to get this lambda and how to get those vectors. So again, let's see the definition of the eigenvectors and eigenvalues. I can rewrite this equation to ax minus lambda multiplied by an identity x equals to 0 vector. All right, and also x is non-zero. X is non-zero. So it means that a minus lambda I times x equals to 0 for a non-zero vector. So this matrix must be singular. That means that there's a linear. It's a linearly dependent. So the determinant of this matrix is exactly 0. So let's think about this example. My matrix is 1, 1, 0, 1 here. So what is the determinant of this thing? It's 1 minus lambda 1, 0, 1 minus lambda determinant. And it becomes 1 minus lambda square minus 1 equals to 0. No. Minus 0 equals to 0. All right. So we called this thing the characteristic polynomial of matrix A. And this characteristic polynomial can get you all the possible values of lambda. And so lambda is the lambdas are eigenvalues, or also we call it characteristic values of the matrix. So here we can solve that lambda equals to 1. And then we can substitute back into the matrix. So A minus lambda I multiplied by x equals to 0, and lambda equals to 1, which means it's the 0, 1, 0, 0 multiplied by x1, x2 equals to 0. And then we can go backwards to solve what's the eigenvalue corresponding to this eigenvector. So you can see that x1 can be anything. 1, 2, 3, -1, or anything, non-zero. And x2 must be 0 here. So that means that for any vector that's parallel to my x-axis will be one of my eigenvector. And all those eigenvectors are corresponding to one eigenvalue, which is 1. Right? Okay. So after so to here, do you still have any questions about that? About eigenvalues and eigenvectors of a matrix? Nope? Great. Then after we know what is the eigenvalue and eigenvector, we can do eigenvalue decomposition. So now we have another more strict assumption that A is now an R by R, an N by N real matrix. And all the eigenvectors of A are x1, x2, blah, 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 to xn. And I assume all those vectors are linearly independent. So that is to say, for if I have the equation a1 x1 a plus a2 x2 plus blah 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 plus 2an xn equals to 0, if I have that kind of function, it's only holding when all a1, a2 to an are zeros. Otherwise, if any of them are non-zero, this thing won't be 0. So this is to say, from x1 to xn, all those vectors are linearly independent. All right. So now I can build a large matrix Q equals to x1, x2, blah, so this is xn. It still will be a n by n matrix. All right. It looks suspiciously like the orthogonal matrix, but it's not, because I can't make sure if I'm picking any two different vectors, they are orthogonal to each other. So if I have dot product between x1 and x2, it's not necessarily to be 0. So this one is not orthogonal matrix. And also, this one is also not normalized, so the length of x1, x2 to xn can be arbitrary. But we can still hold this equation. So what is A multiplied by Q? So A multiplied by Q is basically AX1. This is my first column. My second column is AX2. And to my last column is AXN. So it's still going to be an n by n matrix. I'm just applying A to all the columns of the matrix. So this is a matrix multiplication. All right. And what is AX1? It will be lambda 1 x1, because x1 is one of A's eigenvector. So it has a corresponding eigenvalue. And also I can write all of them as lambda 1 x1. This is a lambda 2 x2, blah blah blah, to lambda n xn. All right. So and then we can write this matrix as x1, x2 goes to xn multiplied by a diagonal matrix. So it's lambda 1, lambda 2 goes to lambda n. And those are zeros, those are zeros. You can verify it by yourselves. It's so the multiplication of those two matrices will be this one. All right. So So this is what? This is my original Q matrix. And I'm gonna write this matrix. This is a diagonal matrix. I'm gonna write it as uppercase lambda, because it contains all the eigenvalues of my original matrix A. So that means that the matrix A times Q can be represented as Q times lambda. All right, and so if I multiply by the and because I have assumption of all x1 to xn are linearly independent, so Q is invertible. So if I times the inverse of Q to the both side of the equation, it becomes the same. And this one goes away because it's identity. Then I'm decomposing my original matrix A into its eigenvectors times the corresponding eigenvalues times the inverse of my eigenvectors. Okay, and then so what? so I have a decomposition of this. So what? So the first thing is to say, because A matrix is similar to this matrix. This is a definition of the similarity of matrices. And I can see the eigenvectors of A and the eigenvectors of lambda are the same. Because the eigenvectors of lambda is basically the diagonal term, and the eigenvalues of A is also from lambda 1 to lambda n. And actually I can prove it, because the characteristic polynomial of matrix A is like this. And then I can always write it as the decomposition of Q lambda Q inverse minus lambda multiplied by Q and Q inverse, and this is identity. All right. So because determinant is also a linear operation, so determinant A multiplied by B equals to determinant A multiplied by determinant of B. So you can get Q and Q inverse out. It becomes the determinant of Q multiplied by the determinant of lambda matrix minus lambda I multiplied by determinant of Q inverse. And those two cancels with each other. It means that the characteristics matrix between A and lambda are the same. So they have the same eigenvalues. And if you still remember one property that I mentioned before, if how to define if a matrix is positive definite. If I have a diagonal matrix, and if and only if all the diagonal terms, this is d1 to dn, di is larger than 0, then I can make sure this matrix D is positive definite. All right. So then, because A can be write as a decomposition of Q lambda Q inverse, and they have the same eigenvalues with lambda. So that is to say A is positive definite if and only if all the eigenvalues of A are larger than 0. So this can be used. This one can be used to test if the matrix property, to test whether this matrix is positive definite. Okay. And lastly, the last topic about the eigenvalue decomposition is an even more special case. So what if A is square, this is my pre-assumption, and real, and also symmetric. So I won't prove it here, but I can say that first, my first conclusion is all eigenvalues of A are real. And two, so there exists a set of eigenvectors u1, u2 to un, and all of them are orthogonal. So basically ui transpose uj equals to 0 for I is not equals to j, and ui transpose ui equals to 1. So in that case, my eigenvalue decomposition becomes u times the diagonal eigenvalue matrix times u inverse. And because the large U matrix is a combination of all those factors, this is an orthogonal matrix, so I can write it as a U delta U transpose. So it's this one is even more beautiful because it has a very clear geometric interpretation of it. Because U is an orthogonal matrix, and so U transpose is another orthogonal matrix, right? And this is to say that for any kind of linear transformation, I can rotate my coordinate system to such a way. And this one is diagonal matrix. And basically a diagonal matrix, you can see it as a scaling matrix. It's scaling your vectors to all of its axes. All right? And then I'm going to scale it using my delta matrix and also rotate it back. If I have a matrix 1, 1, 2, 2, 1, 1. So if this is my A matrix, I will map a rectangular, this is 1, 0, 1, x and y. I will map the rectangular into this case, 1, 2, 3. So on 1, 2, 3. So 1, 1 becomes 2, 3, 3, and then this one becomes 2, 2, 1. So this is my linear transformation. At first, you can't see very clearly whether this linear what this linear transformation is doing. But after this eigenvalue decomposition, you can see that this linear transformation is basically rotate my rectangular for 45 degrees and scale it up in my y-axis and then rotate it back. Right? Okay. What? Sure. And so any point in this coordinate system, like this one is 1, 0. After the linear transformation A, it becomes 2, 1, all right? Because this is 1, 0 times A equals to 2, 1. And I can do this kind of linear transformation for all the vertices in the system. And then you can see that the rectangular shape becomes this new shape in my new coordinate system. All right. So this one is it shears this matrix in both x and y directions because this is the shear matrix, and also scale it in x and y directions too. But we can interpret it in another way. We can have the eigenvalue decomposition of A. A must be, because A is a real square symmetric matrix, it can be written as U lambda and U transpose. No inverse here. U transpose. So this is to say that in order to get this shape, I can rotate my rectangular, my square to this shape. So this is the result after multiplied by U transpose. And then I can scale it up to the y direction. So it makes this rectangle skinnier. And then I'm going to rotate it back 45 degrees back to the original system. So the shear function in both y and x directions can be seen as a rotation, scaling, and rotate back. All right? So this is a very nice thing because if I want to measure, it's always used in those deformable object simulation. If I want to measure what is the deformation after this kind of linear transformation of the rectangular thing, I would say that the deformation is basically scaling the rectangular in this direction. There's no rotation, there's no translation, there's no shearing. It's basically scaling. Right? Okay. I'm writing everything fast because I assume you already have some basic linear algebra knowledge about it. So if you are not clear about anything, just stop me and all right. Right. So I'm stopping right now. Do you have any questions about eigenvalue decomposition? Nope. Hopefully. Then we will have a stronger weapon, a singular value decomposition. Or we just abbreviate it as SSVD. So because we can recap, if I want to get the eigenvalue decomposition of A, so A must be square and real and symmetric. So those are all the assumptions that I made for the matrix A. So what if the matrix is not symmetric? It happens a lot. If you remember the shearing matrix 1, 1, 0, 1, it shears the shape to this thing. This is not a square matrix. Sorry, this is not a symmetric matrix. All right. And I will still assume we are working on the real numbers because for most of the physics-based simulations, we are not so worried about complex vector. But it's also possible that my matrix A is also not square. So if it's not square, there's no way to say whether it's symmetric. It's not even a square. So in the general case, I can have an arbitrary real matrix A, which is an M by N matrix. So I can draw my A matrix like this way. It has M rows and N columns. So in this case, M is less than N, but also I can flip it to draw the case where M is larger than N. All right. So I want to get some similar decomposition of this matrix to see what is the property of this matrix. So my goal, so this is my goal. My goal is to say I want to decompose A into 3 parts. The first one, so this is M by M matrix. The first part is an M by M matrix. It's a square matrix. We call it a U, and also we want U to be an orthogonal matrix. Orthogonal matrix. Like our singular value decomposition for real symmetric matrix. And also, we want another matrix. We call it sigma. So the first M columns of sigma are a diagonal matrix. It's D11, D22, blah 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 to dm m, and all those things are zero. And the second part of the matrix is a zero matrix. It's blank. It's nothing. And also multiply by a larger matrix. This is called V transpose. And this matrix is going to be an n by n matrix. It's also an orthogonal matrix. So if I have this kind of formula, it's pretty much like the eigenvalue decomposition for real symmetric matrix. All right? We called all the vectors in U. So all the vectors in U, this is U1, U2 to UM. So we call those vectors the left singular vectors of A. And similarly, we have the V matrix, which is V1, V2 to Vn. So this is an n by n matrix. It has n vectors. And we called all those vectors the right singular vectors of A. And also, we call the diagonal term, there are m diagonal terms are non-zero from D11 to DMM. And those are singular values of matrix A. All right. So if you just see this graph, so I will put the transpose out, so it's clear to see. If you see this kind of graph, we can say that A is basically a matrix which sums up from I equals to 1 to m. It's dii multiplied by ui transpose multiplied by vi. No, ui multiplied by vi transpose. So this is my matrix A. It can be divided into a constant number with the outer product of two different vectors. All right. So we are just gonna assume it exists. I won't prove the existence of this decomposition here. We assume A equals to U sigma V transpose exists. I have two questions. The first one is this decomposition unique? And the second one is, how do we get this matrix? If it's not unique, and then the question becomes, how do we get one of those decompositions? Right? So we'll solve the first question first. Because you can see that A equals to the summation of I equals to from I to m dii goes from ui to vi transpose, and I can get the first term out. It will be d11 multiplied by u1 v1 transpose plus the summation of I equals to 2 to m, the rest of it, dii ui vi transpose. There's a transpose here, right? So if I flip the sign of ui and vi, they are still going to be unit length vectors. All right? So if I say u1 equals to negative u1, v1 equals to negative v1, this equation still holds. So that is to say, the decomposition of A is at least not that unique, because I can flip the signs of corresponding left singular vector and the right singular vector just to reverse all those vectors. and this decomposition still holds. All right? And also, it can be even worse. What if there are two singular values, they're the same? Let's say D11 equals to D22. And I don't care from D33 to DMNM. So then I can still write it as D11 U1 V1 transpose plus D22 U1 U2 V2 transpose plus from 3 to M DII UI VI transpose. And I'm not caring about this for now. I'm just going to care about the first two items. So, because we know D11 equals to D22, so A becomes D11 multiplied by a vector U1, U2. So this is a matrix. I'm sorry. And multiplied by 1, 1, 0, 0. And multiplied by another matrix, V1, V2, transpose. And plus the sigma of the rest of it. And do you see this one and this one? They are the same. All right, because this is right, this is a U1 V1 transpose, and then that's U2 V2 transpose. And because D11 equals D22, so I just get it out of the matrix. So I will call this matrix, the small matrix, as U hat, and this small matrix as V hat. And what if I have two new matrices? U tilde equals to U hat multiplied by Q transpose, whatever. V tilde equals to V hat multiplied by Q transpose, where Q is a 2 by 2 orthogonal matrix. So, well, what's going to happen here? So the identity, I can simply drop it away. And all I cared about is the value of U hat V hat transpose. All right? And now I have a new UVs. I have U tilde V tilde transpose. It will becomes U hat Q transpose Q V hat transpose. And because Q is a 2 by 2 orthogonal matrix, this term just goes away. It becomes identity 2, so it goes back to U hat V hat transpose. So this is to say, if I discard those original singular vectors U1, U2, V1, V2 with my new vector, like U tilde 1, U tilde 2, which is U hat multiplied by Q matrix. So this is still a valid singular value decomposition. The result will be exactly the same. All right. So now we can say that the singular value decomposition is not unique, but we can still somehow to get one of it that we liked. We can say that if I want to have a singular value decomposition U sigma Vt, we want all the elements in sigma D11 is larger or equal than D22, larger or equal than D33. It goes on and on to DMM. We want it as a positive, non-increasing sequence. So in that case, it's still not unique, because the thing that I proved before, those two still holds. If D11 equals D22, we can still find a different singular vectors, and also we can flip the signs of the singular vectors. It's not a big deal, but we can sort of calculate it right now. So how? How to calculate A equals to U sigma V transpose. All right, because if you were just seeing this equation, it's not that clear. But what if I write it down as this? AVT equals to U sigma. Let me find my notes in my eigenvalue decomposition. So, in my eigenvalue decomposition, I have AQ equals to Q multiplied by lambda, and the lambda is the diagonal matrix. All right. So here, I'm going to be AVT multiplied by U sigma, and the sigma is almost a diagonal matrix. It's a diagonal matrix combined with a blank. So we can write it up. So this one will be the transpose goes away. It's AV multiplied by U sigma, because if I multiply V to the both hand side of the equations and the V transpose V goes away, it's an orthogonal matrix. So it's going to be AV1, AV2 to AVN. And the second part will be U1, U2 to UM multiplied by a diagonal matrix D11, D22 to DMM combined with some zero part. All right. So this is to say, for I goes from 1 to M, I have AVI equals to DII multiplied by UI. And similarly, we can multiply we can transpose this thing. So A transpose equals to V sigma transpose, because this is a I'm gonna still transpose that, it's not a diagonal term anymore, and U transpose. All right, and similarly we can get an idea to say that A transpose UI equals to DII multiplied by VI. I'm gonna do the similar derivation here. I'm just gonna omit it here. So this is to say, when I apply the linear transformation of A to those V vectors, it becomes a scaling vector. It becomes a scaling effect of U vectors. And again, if I map the transpose of my linear transformation A to U vectors, it becomes a scaling of V vectors. So what if I multiply let me see. Yeah. So in the first equation, what if I multiply by an A transpose before everything? So it becomes A transpose AI VI equals to DII A transpose UI. And then I'm going to substitute the second equation into here, because A transpose UI can be seen as DII, so DII remains, multiplied by DII, multiplied by VI. All right? So it becomes DII square multiplied by VI. Now what is this? So now I'm saying that DII square is an eigenvalue of my matrix A transpose A. There's no I here. It maps my VI vector to a scaling factor of DII squared. So I can't find the singular values yet for the matrix A, but I have already know the eigenvalues of my matrix A transpose A. All right. So if I have the square root of all those DIIs, now I have the singular values of my singular value decomposition. And also, you may notice that also now my V matrix is already computed, because A transpose A can be divided, because U V are the eigenvalues of A transpose A, so I can divide it into v multiply by, this is my sigma square. It's not so good to write it as sigma square. I'm gonna just write it as lambda. And v transpose. And we know how to do it. We can plug into the characteristic polynomials to solve all the lambda values, and then we can get all the vectors over here. And because A transpose A is going to be a symmetric matrix, it's A transpose A. If you transpose it, it's still A transpose A. So it's a symmetric matrix. So because this is a symmetric matrix, I can have this kind of formula. Then I can calculate VR value. And similarly, we can have AA transpose. It equals to U. Oh, I'm sorry. And there is a reflection over there. Nah. Okay. So it can be write as U lambda U transpose again. And there is a lemma to show that the ATA and AAT, those two matrices, although they have different dimensionalities, but at least they have the same rank. So the rank, the number of linear independent vectors of ATA is the rank of AAT is the rank of A. And we can prove that all the non-zero eigenvectors of those two matrices are the same. So now we have all those non-zero vectors, non-zero eigenvalues of ATA and AAT. I can basically have the square root of it. And also because we can see if A is square real symmetric, all eigenvalues of A are real. So, right, we can have this one. And also ATA is a positive semi-definite matrix. If you have any vector x, ATA, x transpose, it can be seen as ATX norm of this squared. It's going to be larger or equal than 0. So this is a positive. So ATA is a positive semi-definite matrix. So all of its eigenvalues are positive or 0. So at least we can have the square root of it. So that's how we get the singular value decomposition. A, now A is m by n matrix equals to U for this m by m matrix, and sigma, this is an m by n matrix, and V transpose, and this is an m by n matrix. So we got this same from the eigenvalues of ATA or AAT. And we calculate this one from ATA, and we can calculate this one from AAT. And it is guaranteed to be exists. Okay. And but if you're told to implement the singular value decomposition, please do not implement it this way, because there's a lot of redundant information there. There are better numerical methods to solve this equation. So if you're going to calculate the singular value decomposition, it's still recommended you to use some third-party libraries such as Eigen in C++ or Boost or something like this. Right? Don't implement it by yourself. It will be slow. Right? So yeah. So I think this is the end of singular value decomposition, and we can see some examples of it. So where do we use it? Where do we use it? So the first one, we used it a lot in compression. If I have an image, it's gonna be it's a small image. It's a 256 by 256. This is an image of me, and then the matrix is pretty large. All right, the matrix A is pretty large, but I can have the singular value decomposition make it to be u sigma v transpose, or write it up as sigma I equals to 1 to m dii ui vi transpose. And the dii is sorted in a non-increasing way. So it's gonna be sure that dii is decreasing. No, it's non-increasing, and it's positive. All right. So after a certain point, I actually don't want to get all 256 of my dii's, and let's say 10. And what if the 10 dii's has already the most of the information covered in my picture? For example, in this picture of myself, white space will be a really large component of the picture, and so I believe if there's a vector 1, 1, 1, 1, 1 or something like this, it's we can just choose the singular value of d1, 1 to represent A. And then let's say we restrict m from 1 to 10. The summation of those things will almost equals to A. It won't be the same. So if I sum up I equals from 1 to 10 instead of a 1 to 256, I will almost get the exactly image, and the only difference is some high frequency information is lost. So this is a kind of a lossy compression. When you decompress it, you will not be able to recover all the information in this image, but you will get most of it. And also the second usage is principal component analysis. If you are doing machine learning classes or some other things, you will get a bunch of data points. Okay, so now this is a pretty high dimensional thing, and this is only 2D data, and assume this is an ND data, and I can't draw it on screen. But what is my singular value decomposition say is to say I can have the singular value decomposition of the covariance matrix to see what is the largest spanning of my data. So here, if it's a 2D data, I'll probably point out, so this axis is my largest spanning. And then I can project everything into this axis. So the information lost will be smallest. All right. Also, this one can be used in some collision detection technique. If you have a very large scene, you want to detect the collision between any two particles. So if they're too far away, then there's definitely no need to detect whether those two particles will collide with each other. And we can definitely say, okay, are they collide when I project to x-axis, or are they colliding with each other when I project them into y-axis? Like this, if something are collided together, the projection of them are also collided with each other, right? So maybe just comparing the x and y and z axis are not enough. So we want to compare one axis which covers most of the information, so I can check the collision detection between all of the particles. So maybe I can say that I will have an axis has a maximum spanning of all my particles or all my objects. And I will project everything onto this axis and check collision detection between them. If they collide with each other, then I will do a further collision detection to see where are they colliding, or are they really colliding with each other. So this is also an application of principal component analysis. And the third one is to get the rotational component of any kind of deformation gradient. So I have a deformation gradient f. If anything in the original distance multiplied by f, so this is x, this is fx, equals to something like this. And I want to calculate what is the best fit of rotation matrix between those two systems. There's no one single rotation matrix that you can get from this thing to this thing, right? So that becomes to say, okay, I want to do polar decomposition of F, which made of R and S. So R is a best fit rotation matrix between those two, and S is a positive definite matrix. And this can be seen as a scaling matrix in an arbitrary axis. So how do we do this? If I know F can be decomposed to U sigma V transpose, then I can say that F equals to U V transpose V sigma V transpose. I'm just adding a new identity over there. So what is U V transpose? Because both U and V are orthogonal matrices, U V transpose is still an orthogonal matrix. This is my R matrix. And this one, if you still remember the example that I have, to change the square to something like this. This one is a scaling matrix in an arbitrary direction axis. It's rotating it to some orthogonal axis, then scale it and rotate it back. This is a V sigma V transpose. All right, so this is my S. And then when I finish my polar decomposition, I can say that my best fit rotation is basically UVT. And that relies on singular value decomposition too. Okay, I have 15 minutes, but I don't think I can cover the SVD derivative, so I will stay this lecture just within linear algebra. So I will leave you some time to ask questions if you have any. Yep.
Are you going to post all this stuff online?
Oh yeah, that's true. Right, and the last lecture has already posted on Piazza, and if you register on Piazza, you can see the YouTube video. Right. Okay, so any questions not restricted to this class about homework and about the future of the class? the which part of the homework you don't understand? Well, does everyone here have already taken a glance of what your homework is? Okay, so this homework is going to be the written assignment. If you have an arbitrary spring, this is x1, and this is x2. The homework is to say, define by Hooke's law, the energy of the system x1, x2 can be seen as 1/2 of the stiffness parameter multiplied by the current length of x1 minus x2. And so this is my current length minus the rest length of the spring and the square. So my E is a function. It maps from R6 to R. All right? And then I want to get what is the total derivative of E, or I want to get the gradient of E on an arbitrary point. So you can already see that the gradient of E will be a column vector, which will be a 6, 1 vector. So this is a partial E, partial x1 x, and partial E, partial x1 y, partial E, partial x1 z. And this is a partial E, partial x2 x, blah blah blah. I'm only omitting one thing already. X2 z. Or as I said, you can just take it as a block gradient. All right. So what is this one? This is partial E, partial x1. So when you're taking this gradient, x2 is just a constant that you can omit. It has nothing to do with my variable x1. So I can get the gradient of this thing. It will be a 3×1 matrix, something like this. And also I can get this thing too. It will be another 3×1 matrix. All right. So once you have those things, you can combine them together. So this is the entire gradient of the system energy. And I remember that in a homework assignment, you are also told to get the Hessian matrix of the energy. As I said, Hessian matrix is nothing but a Jacobian matrix of the gradient. So once you have the gradient, you have another formula. and say ex1 x2 equals to x1 plus x2. This is gonna be wrong, but it's still a function. It's a function maps from R6 to R6. Or x2 plus x1. This is not the answer, and but at least this is a function maps from R6 to R6. All right. So you can still you can do the same trick to get the block gradient. To get the block gradient, block Jacobian of this gradient E thing, and finally you can get the Hessian matrix. A. All right. Is that what you are not understanding about the homework? Okay. Okay. Cool. Yeah. So from next week we are gonna start our real classes. You will need to start programming, and you can visualize your results using all the linear algebra and calculus knowledge that you have. And this is I think this is not the last linear algebra and calculus class. You will also encounter something like Lagrangian multiplier, the SVD derivative that I didn't cover in this class, and also the curl and divergence for fluid. But all those things will be covered briefly. So once you go back, just if you don't understand anything, just post it on Piazza, and I will take my time to see and to answer your questions. All right. Thank you. You're welcome. I think it goes well.
Watch it on YouTube.
Oh wait.
Did you decide when you're going to California?
Yep. Okay, 1 hour and 17 minutes. I think this is gonna be
Yeah,
fine.
that's right. Yeah.
Right. Okay. Okay. Cool. 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 I'm afraid it's not recorded.
Excuse me.
I think you have to sign up for some.
All other classes just automatically
Really?
show up.
This one is it?
Yes.
That's great.
Do it
What? Yeah, if it didn't work automatically, I suggest the
because
register.
other classmates they all don't have them.
Nobody. Wonder if there's something I was supposed to do. I don't know. Well, bunch of people just sign up. Right?
Okay.
I also